have each one of you join us, coming together for a shared experience like never before. So, today marks a special occasion where we gather to celebrate, learn, and connect in this digital realm. So, first of all, let me tell you the specialty, the objective of today's session. So, the SEDS community of the Sabra University of Sri Lanka is hosting a series of advanced webinars on the latest technologies. So, as the initial step of that, the initial step of this project, they have organized an awareness campaign to educate everyone on the foundations of these technologies. So today we have all attended the very first session of that awareness program. The topic of today's session is satellites. So I acknowledge your presence in this wonderful virtual gathering. Let's make the most of this opportunity to learn, grow, and build lasting memories together. So we also encourage you to participate actively in the session, share your thoughts, and make new connections. So take a moment to settle in, make yourself comfortable, and get ready to embark on this incredible journey with us. So moving on, it is with great pleasure and honor that I stand before you today to introduce our esteemed guest speaker for this event. His presence here is a true privilege, and we are fortunate to have him share his knowledge, insights, and expertise with all of us. Our guest speaker is a visionary in his field, and his dedication, passion, and commitment to his work have inspired countless individuals and organizations, of course. So please join me in giving a warm virtual round of applause as we welcome our distinguished guest speaker, undergraduate in the Faculty of Geomatics at the Sabaragama University of Sri Lanka, Mr. Hasita Dedunu Arachi, to share his wisdom and inspire us all. Mr. Hasita, over to you.
So, hello everyone. Good afternoon to all of you. Uh, so, so we are here to join the first session of this satellite webinar series that organized by SEDS Sabra. So, as the first session of this satellite webinar series, so I'm going to start with some basic things about the satellites that telling you. So as the first one, introduction to satellites. So let's go. I'm going to start with a definition for satellites. So if we have a definition for something we want to discover, it will be more easy to discover because our discoveration will not be moved to another direction. We can go through our path with a definition. So then I'll talk to you some historical background of satellites. Then I'm going to talk about the importance of satellites in modern life, day-to-day life, like modern life, right? So let's start with the definition. All of you, I think, gathered here know what are the satellites. I have seen those satellites on the night sky also, and satellites. Also, all the satellites. Oh, satellites only the man-made things. Some Some know only the man-made things, but satellites not the only man-made things. Satellites can be natural also, right? Uh, then what are the satellites? So satellite is an artificial object placed in space to perform specific tasks or missions, or a natural object that orbit a larger celestial body, right? Uh, that means satellites can be a man-made, or satellites can be a natural. You know, moon. Moon is a satellite for our Earth, because moon is orbiting the large celestial object. It means Earth, and it has a purpose. You know what are the purpose, and we are making some artificial satellites also in our Earth, and get into the space, then orbit, then make an orbit to it, and make it something to happen. So that is the satellite. Then let's move to another thing: historical background. Historical background about these satellites. So ancient observations. I'm pretty sure that in your childhood you have heard that stories that ancient peoples, they are finding ways according to the star pattern, and they are watching the night sky, and they are finding their way in ships. No, you know that things, and but uh, think that think that think you were there, right? You haven't any knowledge about these things that you are seeing around you in the night sky, like blinking small lights and in the night sky, like very large things also, like sun and moon, stars. You are very curious about those things because you haven't any knowledge. In ancient time, we haven't any these kind of technology, so we couldn't study those things very well. But they were seeing that, they were seeing the night sky. What are those? Like, think sun coming up in the morning and going down. Where it is going, where from it come, like, they were curious about that, so they were implementing some theories. You know, those theories were wrong in that time. Like an example, for an example, think they were thinking that Earth is an circular plane, right? Then they were thinking Earth has an edge. If they were going near the edge, they will be fallen down in like that. So that is it. But most of the early theories, they were wrong. But look at this early theory, right? Ancient Greece proposed geocentric models, while Copernicus introduced the heliocentric model in the 16th century. I think you are a bit amazed now, right? Because 16th century, this Copernicus introduced the heliocentric model, and he has observed that, he has studied that uh, Earth, sun is not rotating around us. We are rotating around the sun, right? You can see this. Wait. You can see this picture, heliocentric model in this picture. This is the sun, and this is our planet Earth. And see, this also, these are star patterns, right? I just bit curious because without this modern technology, how Copernicus able to describe those things, like it's very accurate, I think. Heliocentric model, how he able to find out these things without this modern technology? I'm curious about that. I'm not going to talk about the heliocentric model, not much, because I haven't some limited type in with you. But anyone interested in this model, I think you can go through internet and various references. I think this is very important, very beautiful topic. So then let's move to the historical background knows also historical background. Then the space age, right? This is the day that all the things, all the satellite thing has started, like just this started day, right? Sputnik 1, Sputnik 1 here. I included a picture of Sputnik 1. It has launched by the Soviet Union, Soviet Union, Russian, October 4.
Ask yourself a question. Is this
Yeah.
little electric, my little plug? Ooh, let me get my little plug and plug it in. Oh, maybe I can get an erection one day. Is this the man you are? Are you a little, my little electric plug?
More gasoline, please.
More gasoline, more dead dinosaurs to put inside of my 6.5. Thank you very much. 812 horsepower. Oh, let me get my electricity.
We are sorry for disturbance. Okay, let's continue. The space age, right? The space age. On October 4, 1957, Russian have launched the Sputnik 1. It has no purpose. This satellites have these era satellites has purposes now, like weather satellites, GPS satellites, like location satellites, like those. But Sputnik 1 hasn't any like particular purpose.
Ferrari, 2 days in a fucking tent, you're crying your eyes out. You're not gonna fucking die. Stop crying.
We are very sorry for this disturbance. I think so. Let's continue. This Sputnik 1 hasn't any purpose, but the purpose is to identify how it is going to be like when we are launch it into the space, how it will be orbit around the space, how we can get into that orbit, and how we can get into that this height from the Earth surface. To study that, the Sputnik 1 has launched by the Russian, and this is a remarkable day of this like satellites industry, satellite field. This is the day those all the things have started, right? Then early satellites applications. This is also same as this the Sputnik 1 initially focused on scientific research and space technology testing. This is the same thing that above I am telling. Then expansion of satellite technology. Satellite technology became expanded with the implementing of satellite technology. It has become expansion 1960s onward. Then satellites evolved for device application, including weather communication, navigation, and Earth observation, right? Then ongoing advancements. Satellites continue to play a crucial role in modern life, exploring space, enhancing communication, and advancing scientific understanding. Those are the application now we are using satellites for. Few applications, but those are various applications now. Then let's move. Sorry. Then let's talk about the importance of satellites in modern life. Those are some application actually. Global communication, satellites enable worldwide communication, internet connectivity, and broadcasting, connecting people across the globe. You know these things. Then weather forecasting. You know, weather satellites provides critical data for accurate forecast, adding disaster appearances and climate monitoring. Uh, Now, think that when now these days, you are very you can you know when it is started to rain, when it is starting to sunny day, today, it will be rainy or sunny tomorrow. That also depends on these satellites with their forecasting, right? Navigation. I think this is the more, in my point of view, this is the most important thing. Navigation. We can tell or show someone far away from us the navigation, the position. Now we are on the Earth's surface, right? Like G and GNS systems and like those systems, right? Then Earth observations. For Earth observation, it is also very important. Satellites monitoring the planet, providing valuable data for environmental monitoring, agriculture, and urban planning, right? Scientific researchers, disaster management, and internet connectivity also, and then also the defense and security. Maybe this may be good and also the bad. Satellites also used for these bad work. The war things like. So those are, I previously talked about the very basic things of these satellites, and now I'm going to talk with you about the type of satellites, right? So I divided type of satellites into two, like natural satellites and the artificial satellites. I talk about you earlier, the type of these satellites. Natural, it can be natural or artificial. Natural satellites and artificial satellites. Let's talk about natural satellites first. Natural satellites, moons. Also known, moons are generally much smaller than the planets they orbit. You know about this. You know about our moon. It is smaller than our planet. Also, Neptune, Saturn. Those planets has a number of moons than our planet. Those also moons are similar. Like it is smaller than its planet, it orbiting planet, right? They have spherical or irregular shapes. They have spherical or irregular shape. It is also, the moon, right? Depending on their size and composition, right? Natural satellites have no light. It is the another important thing. Natural satellites have no light of their own, right? But shine by reflecting sunlight. You are know since your childhood, from your childhood, how moon reflect, how moon shines, how moon lighten. Um, sun rays come down to its surface, and its surface reflect that sun rays into our eyes. That's how it's lightened, right? The moon. Then let's talk about artificial satellites. I think in my presentation to you, this is the most important part I'm going to talk with you. artificial satellites, right? I'm going to I have divided these artificial satellites into 5 parts, like lower Earth orbit, LEO, and medium Earth orbit, MEO satellites, and geostationary orbit, GEO, and polar orbit. Also the sun synchronous orbit, SSO. Right. Then let's talk about these satellites. Listen carefully. So first, initially, I'm going to talk about lower Earth orbit. Right. These satellites has a altitude. Altitude, you know, what is the altitude? Altitude means the height from the Earth's surface, right? These lower Earth orbit satellites has 180 to 2,000 kilometer distance range, height range above Earth's surface. So then orbits Earth in 90 minutes, right? Orbit, you know, orbit speed. When satellites start to moving from a point and it comes to that point again in 90 minutes, right? Orbit Earth. But not that's not the actual thing. Orbiting time is 90 minutes. It has 90 minutes to go that round, right? Used for Earth observation, right? Yeah, these lower Earth orbit using for Earth observation, communication, and research, and internet services. Within these purposes, within these users, in my point of view, communication purpose is very, very important with this low Earth orbit, because we want to communicate very quickly without delay, right? If the communication satellite is in the lower Earth orbit, it will be reduce that delay, because signal, the distance that signal has to travel is decreased by using this lower Earth orbit satellite, right? That is it. So that is an advantage of this lower Earth orbit, low latency. That is it, right? Then another important thing, high resolution. High resolution. Imagine this. If you are taking a picture of an object, if you are closer to that object, the resolution, it means clearness of that picture is increased, no? Yeah. If you are far away from that object you are focusing, it's not much clear. That's kind of low resolution. Similarly, if the satellite is in lower Earth orbit, the pictures that taken by these satellites has high resolution. That is it, right? Then some few challenges have in this lower Earth orbit. Orbital debris, right? The orbital debris. Orbital debris means like rubbish, right? This orbital debris is this problem is having by also because of humans, because human making these satellites and spacecraft, and it's launched into the space. Then we can't get it back to our Earth or destroy it from the Earth. So those spacecraft and those abandoned spacecraft and satellites are still remaining in the space. So those are these orbital debris. I think this will be a massive disaster for us in near future. Before that disaster, we need to discuss this orbital debris problem. So because it will be a massive problem in near future, I think. Yeah. And has another challenge, limited coverage. I think again, if you are focusing on some number of objects, if you are very close to that object, you have some challenge to cover the all the object. But if you are far away that few objects, you can easily cover up that cover up those objects. Similarly, this satellite, these lower Earth orbital satellites can cover small area, only small area from the Earth, because it is very close to the Earth, 180 to 2000 kilometers. So it's very near to the Earth. So it has a limited coverage. And then we have to talk about some examples of these lower Earth orbits, SpaceX Starlink, Planet Labs, Dove satellites. And within these satellites, I talked with you SpaceX Starlink, right? If someone really interested in these satellite things, you need to see about this Starlink, how Starlink work. It is very, very beautiful. Actually, it is orbital thing is very, very beautiful. Actually, how the Starlink network speed has grown that much. You have to actually go through this Starlink thing. It is very, very, very important thing to know. Yeah. Then growing industry, the potential for space tourism, right? Space tourism, right? Then let's go medium Earth orbit. Then medium Earth orbit, when you are talking about medium Earth orbit, it has altitude approximately 2000 to 35,786 kilometer about Earth surface. It's also orbit Earth in a few hours, right? It's used for navigation and communication, like this. Especially this medium Earth orbit is very important to navigation satellites. Example, GPSs, like this. Then this has some advantages, right? Than lower Earth orbit. Wider coverage, you know that now what is the coverage, wider coverage compared to the LEO, right? Then longer satellite lifespan. Why longer satellite lifespan, right? In LEO here, right? This orbital debris, because of this orbital debris in the lower orbit satellites, it has very less lifespan. But medium, compared to the lower Earth orbit, medium Earth orbit has a less debris. So therefore, these satellites has longer satellite lifespan. That's it, right? Then challenges. These orbital medium Earth orbit also has some challenges. Moderate latency compared to LEO. Moderate latency because distance has now increased. Signal has traveled more distance than lower Earth orbit now. That like that. Then susceptible to radiation, because these very closer to, not very close, but closer to sun, because then it has covered to those sun radiation and other radiation than lower Earth orbit, right? It has a potential destroyed by these radiation things, and disturbed by radiations, right? Then examples: global positioning system, GPS satellites, like that, right? Then let's move to the let's move to identify what are these lower Earth orbit and medium Earth orbit. You can see this low Earth orbit about 1,000 kilometer. It is very closer to this our Earth, and medium Earth orbit about 10,000 kilometer, right? About 10,000 means from 2,000 to 36,700, right? Orbit means it is a geostationary orbit, like that. I will talk about it later with you. Now this is a image of low Earth orbit and medium Earth orbit. So now, as a third one, let's talk about the geostationary orbit. This geostationary orbit has altitude approximately 35,786 kilometer and above part, right? Earth's equator. Orbit, most importantly, Earth equator, not the surface. Okay, geostationary orbit. I will tell you that why about Earth's equator, not the Earth's surface. Then orbits Earth at the same rotational speed, appearing stationary from the ground, right? It is like when we are like, how I'm telling about that. It is reference to the it is not going anywhere, reference to the Earth, right? It's not going anywhere, but it is also going around the Earth, going with the Earth, not the around Earth, right? Rotational, because the same rotational speed, right? So used for communication, broadcasting, and weather monitoring. Advantages: fixed position allows continuous coverage for a specific area. This geostationary orbit also have some challenges: high latency due to distance, high latency, right? Uh, think 35,786 kilometers and above. Very very high distance, very high distance. So signal has to go that distance and come same distance to the down. So high latency due to distance, right? Limited number of orbital slots. Number of orbital slots are limited. Then I will give you some examples for this geostationary orbit. Communication satellites for TV, internet, and weather forecasting. Vital for long. Then these satellites vital for long-term stable communication links and global weather track. Right. Key role in modern telecommunication and broadcasting industries. Right. It is geostationary orbit. This. Now, this is why I told you that approximately 35,786 kilometers above Earth's equator, not the surface, because these satellites orbit in same plane to our equator plane. It is on the same plane of our equator plane. That is why we are telling that geostationary satellite. That's why it's not going anywhere, reference to this Earth. Same speed, same rotational speed compared to the Earth. That is why we are calling it geostationary orbit. Then another one, polar orbit satellites. It is very important. Polar orbit satellites. Orbital path. It is in here we are we are talking about the altitude, but it is more important the orbital path, right? Passes over or near the Earth's pole on each orbit, right? This orbit always going through our two of poles, South Pole and North Pole, or going near our poles, North Pole and South Pole, right? North-south trajectory, traverse from one pole to the another, providing global coverage, right? These satellites provide global coverage by going through the uh, poles also. Let's think this geostationary satellite. I will show you geostationary satellite. This satellite is going with this path, but he can't cover these north and pole parts. Why? It is not seen. It is very hard to see by these satellite. These North Pole and South Pole. Uh, he can cover these near to the Earth equator, right? Only near to Earth equator. Can understand, I think, right? But these satellites, these polar orbit satellites, I will show you these polar orbits. You can see polar orbit satellites going like this, and Earth is also rotating. So this is how polar orbital satellites covering the whole world, but geostationary satellites not covering the whole world. It's very difficult to cover the whole world by geostationary satellites, but polar orbit cover whole world, right? These polar orbit satellites has altitude. It is various, right? It varies from a few 100 kilometers to around 1,000 kilometers. That's why I told you that altitude is not much important, but it is also important when you're talking about polar orbit satellites. Advantages. These polar orbits also has some advantages. Complete global coverage. Yeah, this is the most important thing. Complete global coverage, right? Frequent travels to specific region. It means it is going through the specific region frequently, right? Then it can be covered. It is covered frequently by these satellites. It means polar orbit satellites, right? High resolution and data accuracy for mapping and monitoring. Very important. High resolution and data accuracy for mapping and monitoring. Mapping. Why? If we are making a world map, these polar orbit satellites are the satellites we are using, because we want to we want to cover the whole global, complete global coverage. We need that, right? Then examples: NASA's Earth Defense Earth the system, EOS. NASA's Earth Observing System, EOS satellites, and Copernicus Sentinel satellites. Copernicus Sentinel satellites, right? These satellites play a crucial role in climate studies, weather forecasting, and natural disaster monitoring. Weather forecasting is a very important thing, and yes, this is a complete this satellites has complete global coverage. Therefore, these satellites, the most suitable satellites, I think, for give very good weather forecasting, right? For the whole world weather forecasting, right? Then essential for understanding Earth's ecosystems, ice changes, and ocean currents, like this. Those are some natural things that can happening around us nowadays. Earth ecosystem, ice changes. How ice is changing now. Likewise. Then this is I showed you this but I will explain this again. And this is polar orbit, how the polar orbit is look like. This is our North Pole and South Pole. This is your geostationary orbit. It's going around going on our equator plane, geostationary satellites. Then this is how polar orbit satellites cover the full globe, right? Right. Then fifth one, sun synchronous satellites, right? Sun synchronous satellites means this is also orbit satellites, sun synchronous orbit satellites. It should be orbital satellites, not sun synchronous satellites. These satellites, when we are talking about these satellites, it is also same like the orbital satellites. We want the most important thing in these satellites to talk about orbital path, similar to the orbital satellites, right? Polar orbit satellites. Then I'm going to tell you about this. Read this for you. Orbital path: follow a polar orbit while maintaining a constant angle with respect to the sun. I will tell you. I will explain you this thing. Follow a polar orbit while maintaining a constant angle with respect to the sun. You are not you don't understand now this thing. Then altitude, typically around 600 to 800 kilometers above Earth's surface. These sun synchronous satellites. Synchronization, right? Cross the equator at the same local solar time on each pass. Cross the equator at the same local solar time on each pass. Each pass, what happened? In each pass, cross the equator at the same local solar time. This synchronization, it is very, very important, right? Sun synchronized polar orbit satellites. So used for Earth observation, and climate research. This has some advantages also. Consistent lightning condition on the face during imaging. Imaging means taking images. Consistent lighting conditions when it has same constant angle with respect to the sun. It has the same lighting condition on the Earth's surface during taking images, right? That is it. I will explain you with the picture. How satellites are operating. This is the orbit. This is the orbit. Now think this satellite is going around this orbit like this. It is not this like this going, and this angle, I will draw this angle. You can see this angle, theta. I will tell you this theta. This is also theta. This angle is stay constant. So seeing constant lighting condition on the Earth's surface at each local solar time, right? In each local solar time, satellite sees the same lighting condition on Earth's surface because of this sun synchronous orbit. So this is another full picture. Sun synchronous, theta. So this angle is still constant. Then these are some advantages of these sun synchronous satellites, right? providing regular, repeatable coverage for monitoring changes over time. Examples: Landsat satellites, Sentinel-2 satellites, and I haven't included the Cartosat satellites in here. Then this satellite is crucial for monitoring vegetation, ice cover, and changes in land use. Wait a minute. Sorry. Uh, crucial for monitoring vegetation, ice cover, and changes in land use. Play a significant role in scientific research, agriculture, and natural resource management. I think you can understand why these satellites are important to these satellites to use in these fields. It is covering whole world, and it has a complete global coverage, and also these satellites has uh, constant lighting condition when taking images of the Earth ground surface. That is why these sun-synchronous polar orbit satellites are very important. Let's go. Then this is another part, how satellites work, right? I'm going to talk with you now the satellites, how it's working, right? How satellites works. Then I divided that the things that I have to talk with you, like ABC, can see on the slide: orbital mechanics and launch and deployment, communication with ground station. I talk these three topics with you. Then let's talk about the first topic, orbital mechanics. Right. For satellite operations, these two laws has used, right? First one, Newton's law of motion. I think the here the all of you gathered here, you know about the Newton's law of motion. I'm not gonna reading for you these Newton's law of motion's three laws, but the Kepler's law. Kepler's law is very important in Kepler's law of planetary motion. Very important when you are talking about this satellite mechanics, orbital mechanics. First law of ellipse. Earth planet's orbit around the sun is an ellipse with the sun at one of its two, right? It is the first law. Then law of equal areas, right? A line segment joining a planet and the sun sweeps out equal areas during equal interval of time, right? A line segment joining a planet, and the sun sweeps out equal areas during equal interval of time, right? That is the second law of Kepler's law of equal areas. And the third law of harmonies, right? It is the third law. The square of the orbital period of planet is directly proportional to the cube of the semi-major axis of its orbit. Semi-major axis, like it is a radius, right? This is the mathematical representation of the third law of the Kepler's law of planetary motion, where T is the orbital period, right? Orbital period means the time that satellites like this. Satellites have the time that want to satellite complete one orbit, right? It's the T, orbital period of a planet. this is the orbital mechanics. Newton's law of motion and Kepler's law of planetary motion has used to operate these uh, satellites and operate in with the orbits. Right. Then it is very important to talk about the satellite launching and deploy. Right. How satellites launch? I think this this thing is known by all of us, right? Satellite are launched into space using rockets, typically from ground-based launch facilities, and rocket stage providing the necessary thrust to propel the satellites into space. Propel and the thrust, that rocket is the fire that has rocket made when it's going to the space. And different launch vehicles are used depending on the satellite size. Different launch vehicles are used depending on the satellite size, weight, and intended orbit. Like Apollo, like those ancient spacecraft also, like those things. Nowadays, Starlink, like that, right? Orbit selection. The satellite's intended mission determines its specific orbit. Example, Leo, Mu, and Geo. Right? You learned about that previously. I taught you. Uh, Orbital parameters like altitude, inclination, and eccentricity are carefully chosen for mission requirements. Orbit selection. Right? First, we will select orbit. What's the orbit we want to take this satellite? What's the orbit we want to orbit the satellites? Leo satellite, Leo or Mio or Geo, or those polar orbits or sun-synchronous polar orbits within this file, right? Then deployment. Deployment. Once a rocket reaches this designated orbit, the satellite is released from the launch vehicle. I think you also, if you are watching some movies related to these space things, you know how satellites releasing from its launch vehicle. I think all of you has saw these things. If you are interested in this space, I'm pretty sure that you have watched some movies like Interstellar. You know now how deployment is happening. Some satellites deploy now. This is the important thing you have to know in this thing. Some satellites deploy immediately after reaching the target. Some satellites deploy immediately after reaching this target, right? If the vehicle reaches the target, some satellites deploy immediately. But while other satellites use onboard propulsion for final position, right? Some are not releasing immediately. Those satellites are use onboard propulsion for final position, right? Then it is released to correct orbit that that they want, right? Then communication with ground station. When we are now, we have taken the satellite into space. Now we want to communicate with the satellite. That is how we getting information from this satellite. So this is the important thing. Why we launched satellite into space? To simply take information. We need nothing but information or raw data, right? With these data, we are proceedings. We complete our informations, and we will do some research from or observation, or we want to if you want to study those, all the things depend on this satellite data and information. So that's why we are launching a satellite into space, right? This is a small this is a very important part, communicating with ground station. This is how it's going. Once in orbit, satellites communicating with ground station on Earth to transmit and receive data. Once in orbit, satellites communicate with ground station on Earth to transmit and receive data. When you are taken it into the space, it has a receiver, right? Receiver and also receiver, right? That is how we get the data from it, by receive. Ground stations are equipped with antennas to establish radio frequency links with satellites. The ground stations are equipped with antennas to establish radio frequency data transmission, right? Then satellites in low Earth orbit have shorter contact duration with the ground station due to rapid orbits. Then geostationary satellites maintain constant visibility with the ground stations due to synchronization of the sun due to synchronized orbits, right? Geostationary satellites maintain constant visibility with ground station due to synchronized orbits. This geostationary satellite synchronized, like it's not going anywhere reference to the Earth. That is how it's synchronized. Then it's constantly visible with the ground station, right? Communication protocols ensure secure and reliable data transfer. Ground station network worldwide providing continuous coverage and data relay. Ground station network worldwide provide continuous coverage and data relay. Then ground stations teams monitor and control satellites, ensure optimal performance, right? Ground station teams monitor and control satellites, ensuring optimal performance. Satellites signals may be received by multiple ground stations for redundancy. You know, redundancy means satellite signals may be received by multiple ground stations. For redundancy means for more accuracy. For redundancy means for more accuracy and more reliability, right? Then ground station location strategically chosen for global coverage and visibility, according to those orbit. Those orbits are the operation of those orbits. They are choosing ground station locations are strategically for global coverage and visibility, right? Then satellite applications. Let's talk about this application: Earth observation and remote sensing. Earth observation and remote sensing, you know, these are like remote sensing means observing Earth and mapping like this. It's also a positioning also, and then communication, navigation, GPS communication and navigations, weather forecasting and climate monitoring, scientific research, military and defense, a lot of, and including these